This is Lab 4, Magnetic Braking with Faraday. For the introduction, the purpose of this lab was to measure how long a falling bar magnet takes to pass through a conductive non-ferrous aluminum foil tube. Then we were to build a computational model using Faraday's law to predict and explain the braking effect experienced. The fundamental physics principles used in this lab are Faraday's law, Lenz's law, magnetic dipoles, and Newton-Silicon law. The models used in this lab is the magnetic dipole behavior model. The results of this lab found that in real life the fall time was 0.25 seconds, while in the computational model it was 0.406 seconds. This concludes that the model can be close but not totally accurate at predicting magnetic falling behavior. So the main physics idea is Faraday's law. It speaks on how the magnetic flux through a loop induces an EMF around a loop, driving a current if the loop is conductive. This in turn creates a magnetic field. The second idea is Lenz's law, where the induced current flows in the direction of opposing flux. This is why the magnet experiences some braking force. The equations used in this lab are Faraday's law, Ohm's law, Newton's second law, and the force of gravity, update formulas, and magnetic flux. So here's all our formulas: Faraday's, Ohm's, Newton's second, force of gravity, our updates of final velocity, final position, and magnetic flux. So the main experiment consisted of a barred magnet and a roll of aluminum foil. The barred magnet was dropped down the roll, and the time was measured for how long it took to go all the way through. And a computational model was used to mimic this. The system is the barred magnet and the aluminum foil, and the surroundings is the Earth. The initial conditions are the magnet has zero velocity in a certain position above the aluminum foil tube. There is no current induced in the aluminum foil as well. So here's the experiment: aluminum foil, the magnet just falling down. So the coding process was very simple, as most of it was already filled out. What I had to do was set up initial conditions of the tube and the magnet. I then had to calculate the magnetic field and the EMF and flux going on. Then I had to calculate the induced current and the sum of the forces on the magnet. This would all come together to form the updated velocities and positions of the magnet. So here's the code, some important snippets, kind of some of the functions I added. So here's the code running, here's my tube, and then how it reaches here, and it goes to terminal right there, which I'll discuss in a second. So the model versus experiment discussion. The model predicted that the magnet would fall down through the tube around 0.46 seconds. In real life, the experiment predicted that it would fall in 0.24 seconds or 0.25. This is a very large gap and can be due to some possible points of error. These points being: the first point of error is the improper dipole moment calculation. The dipole moment can greatly affect how the model predicts the time, and mine may have been done imperfectly. Another point of error is the foil could have some disparities that mess up the experiment. This would be different than the model, which does not have these imperfections. So what if, and what does it mean? To answer the first one, I said that much larger currents would be induced. This would create a much larger magnetic force opposing the force's downward motion. The magnet would fall much more slowly in turn. So for the second one, I said this would cause the paths of the induced currents to be broken up. This would reduce the amount of magnetic braking, resulting in a much faster magnet. So for the conclusion and other questions, which are at the bottom of the lab, I already answered number 4, so I didn't include that. There was actually 3, but I just put it as right here. So from this lab, we can tell that the experiment and model are close in value, but not exact. I think the disparities can be colluded to some points of error. Overall, the lab results are close enough to be successful. To answer the questions, I said the current flows counterclockwise below the falling North Pole, creating an upward magnetic field that repels it. For the second one, I answered if you flip the magnet, the overall dynamics would remain the same. And then the flat portion at the very end indicates the magnet reached terminal velocity. So that is it. Thank you.